All right. So let's continue. And as I said, we are going to neglect vectorial modes because they are decaying and are not that interesting. And I'm going not to cover gravitational waves because that's related to the propagation of gravitation. So the tensorial mode because it's related to the propagation of gravitational waves. So that's not of interest in what I want to cover in the upcoming lectures, which is cosmic structural formation, where gravitational waves are completely irrelevant. Good, so let's consider only scalar components of what we have seen before. So I just write it here again. So we have the perturbation component of our metric, which contains only WE. That's the WE, and Sij, which are minus 2 phi, WE, the scalar component only. Scalar component only. Remember that we split it, and also the vectorial one contains a scalar component. Then we have WES, that's again for the symmetry of the metric, and then we have the tensorial component, sorry, the other scalar component, plus the tensorial component, which was associated to a scalar. Okay, so you see also those guys, vectorial and tensorial one, are carrying some scalar within, and we carry them around. Okay, so we have 2 psi, E1, E, and then we have 2 phi delta Ij plus the Ijb. Okay, where this guy, you see, that's the expressed in terms of a scalar quantity in analogy of what we did before. Okay, so that's the key point. Okay, also this guy are carrying a scalar component. Are we done? Well, not quite, because here we have our 10 degrees of freedom, but now we can choose our gauge. We can choose, we can apply a gauge to simplify our problem and extract only the physical degrees of freedom that are contained in that metric, because there we still have degrees of freedom contained in the definition of the coordinate system, if you wish. Therefore, we apply a gauge. It means that we have a 4 function that describes the coordinate transformation that is in place. 4 functions, because we have 1 for time and 3 for space. These are the 3 the 4 functions that we are going to use to constrain our metric. And we are going to reduce our degrees of freedom from 10 to 6. Okay, so how we do it? Well, we just have, I'm not going to compute the gauge transformations, but you know from GR how to do it. That's what we do. Okay, we just apply our gauge, so infinite transformation to our G mu, to our coordinate transformations. So we are going to have a scalar one, and we have xc equal to cs xc E vectorial, Ce, which is of vectorial function. So this is a scalar component. Then we have, you see, this guy is associated to a scalar transformation, so stretching, if you want. Ke C V equal to 0. Okay? So these are our 4 degrees of freedom. 1, 2, 3, and 4 that we are going to use. So 4 free functions that reduces the degrees of freedom from 10 to 6. For what we are going to have, just as a summary of all of that, we have our G mu nu that contains 2 scalar functions, contain a vectorial component and a tensorial component. Again, only for the scalar part. Okay, so only the tensorial component referring to the scalar quantity that are fully quantified. So we have 2 degrees of freedom, 3 degrees of freedom, and 5 degrees of freedom. Then we have our 4 constraints that lead us to 6 degrees of freedom. One that is Newtonian, that is the guy referring to the 2 potentials, to the 2 scalar potentials. 2 that are gravitomagnetic. The gravitomagnetism that is coming from VE. Okay, remember that VE was at the beginning when I showed the 4 element was mixing the tau, the time, and the x, the space. That's the one referring to frame dragging and to gravitomagnetism. Okay, that's coming up from that term. And then we have the gravitational waves. Which is coming from the tensorial component and is the only one that exists in vacuum among those. Okay? Vacuum, yes, we have gravitational waves. These are the phenomena that we can have. Okay? So now let's be a bit more practical. So that's in general the degrees of freedom, the constraints, and the physics which is coming out of them. We can impose a specific gauge. Okay? For example, we can use the Newton gauge, which is also called the Poisson gauge, which is also called the longitudinal gauge. And it's also called shear free gauge. Okay, it goes under all of those names, and possibly more, I don't know, I know these ones. So how are these 3 functions chosen? They are chosen such that we are going to impose the scalar component of our vector term to be equal to 0, and the scalar function b equal to 0 as well. That's from the tensorial one. So what we are going to have? ts squared, that's only the scalar one. Remember that we are reducing ourselves only to the scalar functions. We have e to the power of t, which is a function of time because of the expansion of the universe, which is capturing. Then we have 2 psi 6 squared t tau squared plus 1 plus 2phi, the ij, the xe, the xj. You see why it's called Newtonian? Because it appears only the scalar potential. And in GR, this would be 1 scalar potential, would be the Newtonian potential. Okay? Then we have another gauge. So in GR, phi is equal to minus xa. But not in general. Then we have a spatially flat gauge. Which is obtained by choosing one of these coordinate transformations such that the scalar potential phi is equal to 0 and b again is equal to 0. To do that, the s square again in only for the scalar component is equal to the usual expansion function given carried by our scale factor. minus 1 plus 2c square the tau square minus 2 WES c the tau the xe plus the ij the xe the xj. Why the name spatially flat? Look at the space components. That's Minkowski-like, just along the diagonal, okay? Why is not called shear free? Because of this guy here. There is a mixture between time and space. And it's activated, it's visible in this vectorial component that manifests itself in frame dragging and therefore the electromagnetism, the gravitomagnetism. Okay? Good. So, bottom line, we split the metric into a vectorial, a scalar, a vectorial, and a tensorial term that we further split to identify all the scalars that are hidden in the vectorial and the tensorial term, and all the vectorial terms that are contained, again, in those two. Okay? Then we said, let's keep track of all the scalar quantities, and that's what we get. We choose a gauge, and these are the two gauges that we can impose. One is this one, and one that enforces this condition. The one we are going to consider in the following lectures is the Newtonian gauge, that we are also more used to. Okay? Good. So let's now attack cosmic structure formation. We know how to split the metric. We know why, in general, we have two potentials, not one, two scalar potentials, and not just one. And I wanted to highlight that because if you're going to study modified gravities, then you know that these are all the degrees of freedom that you need to care about. All right. So we will start with linear structure formation. Well, I'm going to follow basically the steps that we already covered in cosmology, with the difference that I'm not starting with Newtonian hydrodynamics, that is, you know, the set of equations, energy conservation and momentum conservation that are used to describe fluids in a Newtonian frames with Newtonian gravity, but I'm going to do it in a fully general relativistic way, starting with the metric, perturbing the metric, applying the perturbation to the Einstein field equation, linearize the Einstein field equation, and do the same also for the energy momentum tensor. We are going to linearize the energy momentum tensor and solve the conservation laws for matter and the metric, for Einstein field equations, couple them together to find out what is the final result. Okay? So I will do that because, again, so to give you, let's say, the instrument, or let you understand how the steps are done, such that if you then are going to use some more complex theory, you know what you have to do. You know the steps, you just have to do the same. Mathematics is going to be a little bit more complicated, but the ideas are just the one that we are going to see here. Good. So what is the system that we are going to consider? We have a fluid in a gravitational field, or if you want, in a distorted space-time. Therefore, we are going to have our Einstein field equations that describes our field, the behavior of the field, given energy momentum tensor, therefore our fluid, which is source of gravity, and the way around is going to tell what the fluid is going to do under the influence of gravity. And then we have the conservation law, so the equation of motion for describing our fluid. Okay? So that's the set of equations that we need to solve. 4 equations and n equations that in the end boils down to other 4 equations that are even not independent, but are the ones that are useful for the derivations, okay? So this is, if you want, the equations describing G, and these are the one describing the source term mu, and they have to be solved simultaneously. I just recall you T mu nu for a fluid, P over C to the power of 3, U nu, plus G mu nu, and then we have the isotropic pressure. If there would be some shearing component, then we would have additional terms, but we neglect them in cosmology. They're completely irrelevant. So that's our energy momentum tensor for an ideal fluid. That's gravity, that's hydrodynamics. Okay, that's what they are. Then what we do? Nice, these equations are nonlinear, it's horrible to solve them in a fully general sense, and therefore we apply a perturbation approach, which is very useful and very powerful in, for example, describing the fluctuations of the cosmic microwave background, which is very powerful in describing the distribution of galaxies. Okay? Because they are indeed in the linear regime. There are tiny fluctuations with respect to the background. So the distribution of galaxies, for example, or the temperature fluctuations on the CMB, there are tiny fluctuations with respect to a background. So all of that can be used to describe all of this physics, not to describe the collapse of galaxy clusters and the formation of galaxies. For that, we will need some other instrument. So let's do it. Perturbative approach, and we are going at first order, linear theory, okay? Later on, we are going to include also higher order terms, and you will see how equations will explode. I will not even be able to write them on the board. I will use the projector, because the equations, one equation would fill a complete blackboard, okay? But that's for later. So we are remaining now in the linear regime, and we need to perturb. You see, we have the density, we have the pressure, and then we have also these guys, because we have also velocity perturbations. Okay? So we have rho, which is the background plus a tiny perturbation. Again, this delta is not the derivative of the density. This guy just means a small perturbation with respect to the background. Same goes for pressure. We have the background plus the P, and then same for the velocity. U mu of the background plus tiny perturbation of the velocities. So U is going to basically, so the background is basically the velocity carried by the expansion of the universe. Whereas these one are the peculiar motions. Okay, say you have a galaxy, which is two galaxies that are expanding universe, so they go apart one from each other. That's carried by this term. Whereas this one is the velocity of a galaxy with respect to the Hubble flow. Peculiar velocity. Okay, good. Then what else? Here we have the ingredients to perturb our energy momentum tensor, but here there is the metric. We need to perturb the metric. Therefore, we are going to have G mu nu write it here, G mu nu, which is the background metric, Friedman, Lemaitre, Robinson, Walker, and the perturbation that we described in the previous board. Let me write the 4 elements. So we're going to use the Newtonian gauge. A to the power of 2 minus 1 plus 2 c square the tau square plus 1 plus 2 phi delta ij dx e dxj. Okay, that's the Newton gauge. Now, to compute that stuff is a little bit of a pain. Okay, in the lecture notes, I made the derivations for you. I just tell you that the perturbed u is u mu is equal to C1 minus your scalar potential C, and then you have V, which is going to be our peculiar velocity. Okay, and you will see in the notes that whenever you do this stuff, this is already approximated at first order. Okay, because we need to keep only first order term all over the places. So I didn't want to show you that, but anyway. So I show you where you start from. So that's the definition of the full velocity, right? Then we can rewrite it in terms of the proper time. And what we do here? Here we can plug in our metric for interval, okay? The S is the for interval. We plug it, so we get all this stuff. You see, we just plug it here. If we do that, we obtain an equation which is a bit horrifying, and in its full power will contain the 2 potentials, okay? And just to boil it down, will look like that. Where this is the gamma factor, but is modified. Okay? In the perturbation approach, the gamma factor is modified. It's not 1 over the square root of 1 minus beta to the power of 2, the usual gamma factor, but is a little bit longer. Okay? So in the perturbation, the gamma factor is modified. The full velocity is modified because it accounts for the proper velocity and the components in which we split the metric tensor. Okay? But these are just details. There are all, all the mathematics is spelled down in the lecture, so just have fun with it. And what we do, we just get our perturbation and boom, 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 boom. We plug it in all over the places. For our metric tensor, T mu nu is equal to T mu nu for the background. So this would be the homogeneous fluid that we used so far in cosmology. Therefore, it describes only, it's relating only to the average density, the average pressure, and the average velocities. And then we have the perturbation mu nu, where T1 mu nu looks like rho, after you do all the steps, delta 1 plus Cs to the power of 2 u mu plus 1 plus W delta u mu plus u mu the u nu, and then there is the sound speed. That's the delta the mu, mu. Where, in this expression, I defined the density contrast. So that's the delta with this curly. So that's this curly delta, as you can see here and there. And this is depends on space-time, and is defined as the perturbation of the density normalized with respect to the background. That's the density contrast. So that's basically rho x mu minus the background with respect to rho delta. And you know that this guy, in the linear regime, can be written in this way. So we have a density fluctuation at the time 0, which is growing or decaying with respect to a function delta t. That's the growth factor. Okay, that's in the linear regime. Density contrast, and is the growth factor. That's the growth factor. Then, since we are in the mood of defining stuff, later on, you don't see it here, but later is going to be convenient to introduce this quantity, which is just a definition, which is the divergence of the vector field. They are important because these are the scalar quantities that we need to solve for our equations. Okay, so these are the quantities that we want to solve for. So we want to know what are the fluctuations of what are the amplitude of the fluctuations with respect to the background, and we want to know how the matter is going around with respect to the Hubble flow. Okay, and that's important because if you have an overdensity, if you want to trace the overdensity which is growing, what happens to a point for the density to grow? You need matter to collect, right? What's that? A velocity flow. And they're both observable. Because this one we can observe, for example, by looking at the density of galaxies, which is not homogeneous. That's unobservable. Or we can see the velocity that is associated to the formation of those structures, okay? Which is unobservable through spectroscopy because we can measure the velocity with the Doppler effect, right? So they're both observable and they're both important. Then, once we have that, we need to linearize the equations. So we have our linearized Einstein, we have our linearized energy momentum tensor. Now we need that we can plug it here to get linearized hydrodynamical equations. And we have to do now the same for the Einstein equations. Okay, let's do that. So we have our G mu nu, which is going to be G mu nu associated to the background. So the metric, it contains the metric of the background plus a perturbation term. There will be higher order terms that we neglect. Okay, so that's the only one that we want. And the Einstein field equations are going to be the 1 8 pi g over c to the power of 4 t mu nu for the background. We already, 0. So we already know the solutions. And what is going to be relevant are the one for the fluctuations, for the one associated to the perturbations. Okay? So what we do, we plug in here the perturbed metric to compute this monster, and then we plug in here these components here. And in the process, we always must keep only first order terms. All the second order terms or higher terms have to be neglected. I will not do the steps because it will take forever to compute, for example, the Christoffel symbols and all of that to compute our G mu nu. And therefore, I just give you the results. Okay? But you know what you have to do. You plug in these guys, plug in here, keep first order term, and in the end, you end up with these 4 equations. Which are square phi plus 3 h c minus phi prime equal to minus 4 pi g. Well, I wrote gr, but actually, anyway, a to the power of 2, 0. Then we have d phi prime minus, let me write it here so that we always have them. Time is up. So h c equal to 4 pi g a to the power of 2 1 plus w rho theta. Then we have c equal to minus phi. Okay, so that's coming out from Einstein field equations, the fact that we only have one potential. And then we have, but if you have an equation of motion for your field which is not this one, that's not going to happen. Okay, modify gravity. And we have phi dot dot plus 2h phi minus h psi prime minus power of 2 plus 2 psi prime phi equal to minus 4 pi g a to the power of 2 c squared delta rho. So we have this equation. That's the mu nu, that's the equation 0, 0. That's the equation 0 e. That's the equation I j, and that's from the equation e e. That's with the I different than j. Okay, only the I and j components. These are your Einstein field equations. You have these 4 equations. And then in the next lecture, we will do the same for this guy. Okay? So that's, let me recap because it's time to go. Okay, so what are we doing? In the previous lecture, so in the previous boards, we got our metric, we introduced a perturbation, and we split the perturbations into scalar, vectorial, and tensorial components. Out of this vectorial and tensorial component, we identified scalar quantities that are contained by them, that are described by them, and we keep them. Okay? If we keep them, we get a metric term that depends on them, but then what we do is to neglect the vectorial components because they decay, so in structural formation they go to die out, irrelevant, and we also neglect the tensorial ones because they're associated to gravitational waves. Okay, then in the context of structural formation are completely irrelevant. Okay. Having that, we have our perturb metric, which is this one in the Newtonian gauge. Then, of course, we are linearizing our field equations. Therefore, we need also to compute the perturbation term for our energy momentum tensor. And the perturbation component only is this one. Once we have the 2 perturbations, we just have to compute explicitly our energy momentum, our Einstein tensor explicitly, this guy explicitly, which is this one here. And then here in the next lecture, we are going to compute also the equation of motion for matter given this expression. Okay, therefore we are going to have the 4 Einstein field equations linearized. We are going to have other 4 equations for the energy momentum tensor linearized, and we are going to combine them together to obtain equations that describe the distribution of matter across the universe. Okay? Close to the end, I'm going to go back to the Newtonian limit. Okay? That's because the Newtonian limit describes very well sub-horizon scales. But all of these mathematics and the formalism that we're going to cover works perfectly in outside the horizon, within the horizon, and in any, taking into account the full GR power, and is necessary if you want to modify gravity. Okay? Good. So let's continue next time by linearizing the energy momentum tensor conservation law, combining them together and get all the cosmological interesting results. Good, thank you very much. I'll see you in a bit for the seminar. Depends on you. When do you want to meet? 2:30 or 2? Okay? So let's do it at 2:30.